welcome to the parallel SQL presentation. Let's see, let's go on to the next slide. My name is Joel Bernstein. I'm a Lucene Solr committer. I work for a company called Alfresco, and I work and live in NYC. A quick slide about Alfresco before we get started. Alfresco is an open source enterprise content management system. It is a system of record for documents, and it uses Solr for search. It's got 1,800 plus customers and 11 million active user accounts. On Alfresco's document level access, Alfresco has a pretty modified version of Solr that has all kinds of interesting features. It has document level access control. It has an eventually consistent model for replication. It's transactional. It has a multi-master model for replication, and it does distributed search and faceting coming with Alfresco 5.1. Okay, so on to the main agenda. So SQL Unleashed and SQL Under the Hood. So with SQL Unleashed, we're going to cover what the SQL interface can do, and SQL Under the Hood, we're going to cover how it works. So everything we're going to cover is already in trunk and ready for 6.0. So I'm not sure when that's going to release, but hopefully sometime soon. So one of the questions that people have asked me over and over again is why SQL? Why bother? This is a lot of effort. And I've changed the slide like 10 times. But what it boils down to mean, I think the most compelling reason is that Solr has become very complex. And it's becoming more and more complex all the time. And the streaming API adds to that complexity. So now you can stream, you can do facets, there's multiple different types of facets, and all kinds of different ways to make things perform better. And we're about to get much, much more complex when distributed joins come in. And it changes, ratchets things up a lot. And so with SQL, we have an opportunity to create a situation where we have an optimizer that hides that complexity from users. So basically, you can type in a SQL query, and the optimizer will pick the proper query path under the covers to use whatever features are needed. I think that's a very powerful thing, and relational databases have been using that technique for years. So the SQL interface has some high-level things that we can look at, and we're going to dig into these in more detail. But basically, it supports SQL over MapReduce, and the point of MapReduce here is basically to support high cardinality aggregations and to support distributed joins. And these are things that are hard to do without MapReduce. And then there is SQL over facets. And SQL over facets, are high performance, and they do aggregations, using facets, and they're for moderate cardinality. And it also supports SQL with a search predicate, which is a much more effective, or I'd say a powerful predicate than most relational databases have. And SQL is fully integrated with Solr Cloud, which means it is now a feature of Solr Cloud. So when you say Solr Cloud, it involves SQL. Okay, so we're going to get into the syntax of this. And the first syntax you can look at is there's limited and unlimited selects. And the key to this is basically that with unlimited selects, you get the entire result set back, which is somewhat unusual for search engines, but the architecture supports that. And with limited selects, you don't get the full result set back, but you can do things like get scores and get text fields and get all stored fields back. Okay, you can also do order bys, which are pretty straightforward, but for this, what's nice is that if you do an unlimited select, you get to sort the entire result set. So millions of documents can come back sorted. It also supports a phrase searching within the predicates. So basically, in this example, there's parentheses around the hello world. That's doing a phrase search. So then it's a full text search, which is a nice thing that most relational databases don't have. You can also do Boolean searches within a field. So in this case, there's parentheses inside of the single quotes, and that becomes a hello or world. So basically, that is a Solr syntax query, which is much more in depth than you can do with pretty much any relational database. It supports a range query, just using the range query syntax. It looks like that. It supports arbitrary Boolean clauses. So in this case, you've got a couple of different clauses. One's doing a phrase query, the other's doing a range query. And so you can just do basic, complex Boolean SQL queries. It supports select distinct, which is a form of aggregation, and you get the distinct fields from a table. And this is where you start to get into the different implementations that are available. So there is a MapReduce implementation where the tuples are shuffled to worker nodes, and the distinct operation happens on the worker nodes. And then there's the JSON Facet API implementation where the operations are pushed down into the search engine and you get higher performance. And you would use MapReduce for very high cardinality fields that you want to do distinct on. And you would use the Facet API for using high QPS use cases where you have moderate cardinality. And so this distinction between shuffling and pushing down is one of the key decisions you have to make in a parallel computing environment. Which pieces are you going to shuffle? When do you shuffle, and when do you push down? And in general, you shuffle for high cardinality, and you shuffle for distributed joins. So I call it parallel relational algebra, but in our case, it's a lot of distributed joins is the reason to be shuffling. And then you push down for performance. So move things. You don't have to move data all over the place. You move the operation into the search engine itself. It supports high QPS, but not as high cardinality. And with the SQL interface, you have an aggregation mode, which has a flag for basically MapReduce or Facet. It's available on the JDBC driver and on the HTTP interface. Okay, so now we have our first set of aggregations. And these are simple stats, and these are without a group by. And basically, this allows you, to generate, use aggregate functions and pull back results. This uses the stats component under the covers, and the initial release supports, count, sum, average, min, and max. And in this case, the aggregates or the logic is always pushed down. So we've made, the SQL interface that says, look, there's never a need to shuffle here, at least with these functions. And so we push down. So it's always going to be very fast. Then there's aggregations, there's group by aggregations, and Eric covered some of this. But basically, it's a pretty full group by, spec. You can do, complex halving clauses and sort by the output of a function field. And it supports both MapReduce and a JSON Facet implementation. And the key thing on this is that with MapReduce, you can do pretty much infinite cardinality with multi-dimension aggregates, which is a nice thing to do with big data. It ships with a JDBC driver. It's already in trunk. It has pullable connection and statements, so you can plug it straight into your Java application. It's Solr Cloud aware. Like I said, it's actually integrated completely into Solr Cloud. So if you use the JDBC driver, it load balances for you, so you don't have to worry about that. It always pulls, a node that's alive and sends the SQL query to it. And the connection class has the aggregation mode switch, so between MapReduce and Facet. All right, so that's it. So that's the basic capabilities that are going to be in 6, unless more get done between now and then. So the next section kind of covers how things work. We're going to spend a lot of time talking about the parallel pieces of it, less about the Facet piece of it. So the first thing you have to do is parse the query. And the Presto SQL parser has been embedded in Solr. And the Presto SQL parser is put out by Facebook. And its job in this situation is to take SQL queries and parse them into what are called tuple streams. And these are the streaming API, base classes. And the tuple stream basically, let's see here. Okay, so anyway, so the streaming API is the general purpose parallel computing framework. So what you're doing is you're compiling SQL statements into the streaming API, the basics of this. And then the parallel computing framework on its own, has different pieces to it. So we're going to kind of go through those pieces. And so there's shuffling, there's worker collections, there's the streaming API, there's streaming expressions, and there's parallel SQL. And each one of these things, build up, to provide more, functionality for parallel computing. So shuffling is, something a part of MapReduce, and basically it's sorting and partitioning of search results. And the way Solr does it is Solr pushes down shuffling into the search engine, which is different than a lot of other shuffling products. And it does it using, so for sorting, it uses something called the export handler, which stream sorts entire result sets. So when I say stream sorts, it means that basically, it can, without having everything in memory, it can go ahead and sort everything. Basically, if you have 20 million documents, it will stream sort the whole thing. It never uses disk. The hash partitioning QParser plugin is what's used to do the partitioning part of the shuffling. And basically, this is a filter. And so, it partitions in arbitrary fields. So these two combined, low-level pieces of Solr are the things that actually do the shuffling. Tuples, which are search results, they stream immediately. So when you do a query, the shuffling happens instantly. So there's no delay at all. And so that's a pretty interesting feature of this. And also, it never spills to disk. So it just shuffles, things are going immediately to worker nodes. So it can be fast. So you can be doing instant MapReduce, instant SQL queries. The bigger your cluster, the more you can push, the faster you'll push. And another really interesting feature of this is that all replicas shuffle at once for the same query. So with Solr Cloud, typically, you get one replica per shard, gives you the top end documents back and they get merged. With parallel SQL and shuffling, all replicas shuffle at once, and there'll be an example of that. So here's a quick picture of a shuffle. And in this case, the client is sending a request to 2 worker nodes. We haven't covered workers yet, but we will soon. And each of those workers then are going to get shuffled 1/2 of the result set. So basically, each worker is given a query. It's the same exact query. And then those workers, they go out to a Solr Cloud collection, and each worker will contact 1 replica in each shard. And since there are 2 workers, you'll see that each replica in each shard is actually getting hit in this query. And then what comes back is tuples that are sorted and partitioned to the workers, and they come back, start flowing instantly, and the workers can then begin acting on that data, doing whatever operations are set to do. Okay, so worker collections are a new feature of Solr Cloud, and essentially they are designed to handle streams that come in and perform operations on them. And you can kind of think of them as like Spark workers in a way. And basically they do not have to hold data, but they can hold data. So you can make them, just basically spin up a collection, leave it there, and then send jobs to it basically. And the search results are shuffled to the workers. And the only thing that the Solr Cloud collection needs to have configured is the stream handler, which is configured out of the box. So basically, you've got the stream handler, which knows what to do with these requests. And then you've got the streaming API, which we've talked about. But basically, the streaming API harnesses the shuffling and the workers. And it is the code that the workers run. And so it is designed to do real-time MapReduce and parallel relational algebra. That's its main goal in life. And the design of it is very, very simple. It's one of the simplest APIs you've ever seen. And there's a class called a tuple stream, and it only has a couple of methods on it: open, read, and close, basically. Those are the important methods. And the low-level tuple streams will make connections, and then you actually start reading tuples from them. And then the way that you transform streams is you decorate them with other tuple streams. So it's very similar to java.io, same exact paradigm. So basically, the programming of this is much simpler than MapReduce and actually much more powerful than MapReduce. So when I say MapReduce, it's really, the only thing that's MapReduce-y about this is the shuffling. Okay, so the types of transformations that occur that, or some of this is already in trunk and some of it can still will be coming, are things like group by, roll up, union, intersect, complement, join. So these are the basic, relational operations you need to do to build a, search engine, not search engine, to build in a an RDBS. Okay, so streaming expressions is one of the coolest part of the system. It was contributed by Dennis Gov, and basically, what it is, it solves a problem that the streaming API had. It had two problems. One, the streaming API is Java, so you had to be a Java programmer to use it. And two, in order to actually transport these tuple streams, these classes that have the instructions in them for what to do, to a worker node, it was using Java serialization. So what the streaming expressions are is it is both a query language, a string query language, which is essentially a parallel computing query language, and it's also a serialization format. So it solved both problems at once. So you can write in basically a query that gets compiled to the streaming API once it arrives on the server. And so now you don't have to write Java to do parallel computing on this. You just can write a streaming expression. And then when it's time for those streaming API classes to get sent to worker nodes, they serialize to streaming expressions and are sent there over the wire as these queries, basically. So it's bidirectional, it's very cool, and it's probably going to be in part of pretty much everything we do with it. The SQL interface uses them a lot. Okay, so the last head of it, and kind of like the tip of the spear, is the parallel SQL, which uses everything. And the way that it works is that a request is made, and it has a SQL statement, and that SQL statement is compiled to a tuple stream. And that tuple stream basically is the streaming API. And that tuple stream is the query plan. The tuple stream is then serialized to a streaming expression. So that is the string expression, the query language, and it is sent to worker nodes. Very efficient way of sending it to worker nodes. The worker nodes translate it back to a tuple stream. So now it's back to the streaming API, and then the worker nodes only have to know, open the stream, read the tuples, and return them back to the caller. And it's that read is where the transformation occurs. And the reason why it's occurring is because you have decorators that are doing things on the read. So that's the whole model. That's the whole thing. So it's all based on the decorators. Okay, so here's a nice little slide that shows a SQL statement that's being translated to a streaming expression. And you can see that this is a group by aggregation statement, and it becomes two expressions. And you can see there's a search expression, and then the search expression is decorated by a roll-up expression. And so basically what happens here is that there is the group by has, it's grouping by this str_s. And you can see that the search function has a partition keys, is str_s, and it sorts on that. So basically the shuffling is built into the search function. And when that gets called, it actually will automatically partition and sort. And then the roll-up stream wraps the search, and basically, so when you open up the roll-up, it's going to open up the search, and it will do it, and each worker will get its partition back, and it will roll up, and what will come out of that is actual aggregates rather than tuples, so individual tuples. And this is an example of a parallel SQL shuffle. And so what's happening here is the client is sending a SQL query to the SQL handler, and then the SQL handler is compiling that to a streaming expression. That streaming expression is sent to the worker nodes. The worker nodes then turn it back into a tuple stream and open them up, and once they open, each worker is going to contact one replica in each shard, and get 1/5 of the search results because there's 5 workers. So in that case, you'll see that every replica is being contacted by some of the workers. So in each one of those replicas is streaming a partition of the results, and it's streaming it back sorted and partitioned back to a worker, and that is happening instantly. Okay, so immediately. So this is immediate, MapReduce going on, and then essentially it's once the data comes back to the workers are able to basically read the streams, and whatever those decorators are doing is what pops out of it. And so that's basically the design of the whole parallel SQL system. These are the key JIRA tickets. There are many JIRA tickets, so I think there are too many to list, but these are key ones to start looking at. If you want to contribute right now, the best way to do it is to look at the test cases that are in these tickets and see the test cases lay it all out. You can see exactly how the stuff works. And in the very near future, there's going to be significant documentation generated for this so that people can just start using it and working with it. But that will be in the next couple weeks. Getting involved, this stuff's in trunk, it's releasing in 6. We can wait till 6 or you can get involved now. All the streaming API stuff is client code. It's all under Solr J. That includes the JDBC stuff. And there's a new package called solrj.io, and solrj.io is kind of the branding of this. So you'll see that more and more. Patches are welcome. Dennis, he basically just started, contributing and started taking a look at it, realized the value of it, and brought his stuff in. Testers and feedback are badly needed, so I would encourage people to test this stuff. So that's really it. So I kind of raced through this, just because I'm not, a professional presenter. But we have plenty of time for questions now. So if anyone's got them, let's hit them. Yeah. Yeah, you don't have to actually though. So if you don't, the query itself, let's go back to this slide actually. So here it says a collection. So you see the first parameter to search is collection. That will just say connect to a collection, and however many shards are in that collection, it will get the job done. So you could have 100 workers talking to 5 shards, or you could have 2 workers talking to 100 shards. It would just automatically do it. It doesn't need it. Yeah, I could go into more details, but it's just not. It doesn't come up as an issue. So the way the partitioning works, everything ends up in the right place. And this stuff is still a very shallow look at this. I mean, we could teach 2-day courses on this to get the real details of how this is working. But this is the high level of how it works. And the takeaways from it, hopefully are just that it's something to continue looking at.
They're pushing it to the worker node to do the signing out. The worker node needs to know the zookeeper details to say where the shards are, and then do the partitioning, or?
So in this query, there's a couple of things going on here that's not shown. The worker nodes, there's a stream called a parallel stream. So if you wanted to do this in parallel, you would essentially wrap the rollup in a parallel function that then tells you where the workers are. Okay, so there's a level of indirection. So this actually, the way this is written, won't actually go to worker nodes. This will just go directly to the shards and run. If you put a parallel stream around it, then it will redirect it to the worker nodes, which will then do the work.
Can it be done without the cloud mode?
No. No. So this is a feature of Solr Cloud, period. Yeah, and I mean, you could hack at it to make it do it, but by design, this is meant to be large systems. We're talking, in the end, this is geared towards big data warehousing projects that would need a lot of servers.
But in Solr, there's a way to actually tell these are the shards on these workers. So you can give a path shards equal to give all the.
Can't do it with this. So you could plug stuff in that would do it, but out of the box, it does not, and I have no plans, or I don't see the community getting behind that. So I think that this, you know, in the end is going to get more, it's only going to get more embedded with Solr Cloud, just put it that way. So when we start doing the JDBC driver in earnest, we're going to have to know a lot about, you know, the catalog and the metadata of things, and a lot of that stuff's going to come out of Zookeeper. And so, you know, more and more it's going to get drilled into Solr Cloud. Yep. So that's what happened. So this is meant to be request and response, and you know it should. You know the good thing about this is because of Solr Cloud, if it will at least pick a live node, and if it dies in the process, then you're going to get an error, and those errors will trickle around, and everything will stop, and that error should be benign to the service, but then you reissue. Okay, so none of the SQL is in 5, none of it. So there is pieces of the streaming API, but the streaming API had a error handling piece that did not make it back. And without that error handling piece, you're going to be really hard pressed to make it work because you're going to get back errors you don't understand. So the nice thing about this is you get back beautiful errors. Like it tells you, exactly what went wrong. And this actually has a mechanism for propagating errors all the way through from the base, search node up into the workers, back to the client. So all these tiers needed to be, the errors need to propagate through. And without that, you're going to be searching through every tier to try to figure out what it is. So you can play with it in 5, but I don't think you can make it work. I don't think you'll be able to build anything out of it. So no, it's not known. I think the big push on it, this will actually help push it, but I think the big push was Java 8. So there's other features that people want in Java 8, so hopefully it's soon. If it drags, then we will seriously consider swapping out Presto for Calcite. Calcite was the other option, and Calcite is what's used by Drill and by Hive, and that is for Java 7. But there were things that I liked better about Presto, so ideally we'd stick with it. Hey. Yeah, there was one thing that I liked better about, so Calcite was more demanding about integrating with their other features. So these things are huge projects. Presto and Calcite are massive, massive projects. And Presto was happy to strip out their SQL parser and make a Maven project out of it, and you can use it as is without touching anything else. Calcite really was not so happy about it. So you actually have to import Calcite core and then get around the fact that it wants you to do a whole bunch of other things that you don't have to do. But there is a patch with it working, so I was able to get it to work. I just felt more comfortable with Presto. Yep. No. So there are 2 implementations. So there's a MapReduce implementation and there's a Facet implementation. The Facet implementation uses the JSON Facet API. So, and also for simple stats, it uses the stats component. So the optimizer will choose whatever underlying mechanism is there. And it's never my goal to rewrite low-level stuff in Solr. My goal is only to pick and choose which pieces to use when. Yeah, this may be the way that you use it, but under the covers, it's still going to use the JSON Facet API. So someone like Yannick is going to keep on writing the JSON Facet API, and then I'll keep on integrating his stuff into this, and it'll get used. And I don't think he cares whether you actually type in that, but I think what he is interested in is that that it can do both, so that it can do both. And this is actually a really kind of cool thing because there aren't a lot of engines that can actually push down this type of analytic stuff into the engine and do MapReduce. You could probably count them on, 2 fingers, the types of engines, the amount of engines that can actually do that. Okay, so if you're using the facet stuff, so let's say you're doing aggregation mode facet, it's just as fast as using, facets on their own. It's doing, there's just a very small amount of work on it. If you're using MapReduce, it depends on how much you're shuffling. So basically what it boils down to is that what you need to do first of all, the shuffling stuff is designed for big clusters. And so the idea would be to have, a lot of shards, a lot of replicas, and then a good number of workers, and then you can push literally hundreds of billions of documents per second. So you can do sub-second stuff, and then at that point, the bottleneck will be the network. And so we need to work on that. But so there's no easy answer to it, but you could scale this and still be fast. Yes. So that's a good question. I think when it gets down to actually the predicate, the Solr predicate, it's likely we'll leave that to be as is, so that people can just have the power to just type in whatever predicate they want. And that's where, you're really good. People who know how to write queries really well. People who can write, QParser plugins can put a QParser plugin in there. So you can do really fancy queries with that. Yep, Otis. So Elasticsearch aggregations is very similar to faceting, where everything is pushed down. So it's all pushed down into the engine. There is a product called Crate.io. Are you guys familiar with Crate, anybody? So Crate, am I done? 10, okay. Crate actually does a hybrid of this where they push down the facets, but then they actually shuffle the intermediate results to workers. So I would say Crate is part of Elastic's community, part of their, world. And it wouldn't surprise me if they, Crate and Elastic one day became the same company. But right now, I don't think there's really comparable to a full shuffle. So this is probably the only open source search engine that does a full shuffle. So Crate is shuffling only the interim aggregates. This is shuffling everything. Yeah. So it uses the statistics module. Let me go back to that slide. Only for very simple here we go. So only when you don't have a group by. Okay, so if you don't have a group by and you never have to actually do buckets. So faceting is all about buckets. This is oh, I think I lost it. That's all right. So now it's back. So you don't have to do it. It was the first approach. The other thing about this is that if somebody comes in and says, there's a better way to do this, we can just change it. It's under the covers. So this is my first cut at how I thought maybe it'd be best to do it. Any other questions? Yeah. David. Okay. Yeah. Okay, so it's very flexible in that you can create a collection just for workers if you want to. You can say, here's a collection, there's 100 nodes in it, and they're just a worker pool. Or you could have a collection that has data in it and make them workers too. And there is a class called the parallel stream. And what the parallel stream does is you give it a collection and you give it a number of workers and it just sends data to them. So it can be anything in the system, it just has to be a collection. I didn't really get into the parallel stream very much in this. Yeah, so workers don't need much because they're basically a CPU and they're just taking in streams. And unless we start doing things where we're holding on to more memory, they don't even need a lot of memory. So workers could be very light. You know, Solr replicas and shards would have to be as heavy as they would need to be in order to hold the data that they have and do, if we're pushing down, if we're going to do facets, you would need your normal caches for that. And also you need caches to do the export because it's using doc values. So, still your Solr nodes need to be fairly hefty. So it's only the worker node that would have a different, way of looking at it, which is actually in some ways worth it, a good enough reason to have workers in a separate thing because it could be much cheaper. So, yep. The network will be the bottleneck very quickly. So what's going to happen is you're going to have all your replicas pushing data as fast as they can, and some of them, I've been able to get, data pushing at, 700,000 records per second off of a single node. So if you have that pushing, all of a sudden your network's flooded. And my first, reaction to that is, first of all, what we're doing right now is we're doing JSON, and we have to get away from that. So we got to do something that doesn't include the fields with it. We got to do something binary, and we got to do something small. So the next step on this is to have a lot less data on the network, and so we'll get like, probably 100%, gain just by getting away from JSON. And then eventually the network will be the bottleneck though. That'll be it. I think we'll reach a point where we can't get any further than that, and we'll have to have hardware. So, and actually, maybe Ani can talk about it. These guys have very good network at Bloomberg, like superb network setup where you can send lots of data. And maybe, the idea is eventually to have very good network around this. Yep. Okay, so that's actually there, because the core pieces of this, particularly shuffling, is pushed down, the concept of rack awareness goes away. So let's say with Hadoop MapReduce, you want to say, oh, I want to get my mappers closer to the data. There's nothing like that here. Everything is pushed in, so you're already on top of, you're in the data. So there's no real need to do it. Now the workers, you could say, I could see why maybe you'd want to keep the workers close by, but the other thing is I don't anticipate this being quite as big as like having thousands of servers. So I would imagine you could probably get this all on the same network without too much trouble. And also this is designed for the Solr community. This is not designed as a replacement for Hadoop or something. This is something that the Solr community can use. There's lots of people in the Solr community that don't have petabytes of data, but they still have lots of data. And I think it's a good alternative to something that is maybe massive like Hadoop. Yeah. That's all we've got now. Okay, so one of the things is percentiles are already inside, they're already implemented in the JSON facet API, so they'd be easy to do. But I think I was being pragmatic and just decided to cut it off so that I could get things out. And then one of my main goals was to put out enough that it would be useful and that other people would want to contribute, because eventually I'm going to run out of gas. So when other people start contributing, then it will start to get more stuff coming in. Yep. Nope. So I can tell you that that's a very high priority. So Alfresco is very interested, that's who I work for, very interested in this JDBC driver. It's going to get worked on by resources at Alfresco, by myself. I could see other, Lucidworks having a considerable interest in it as well. So I think the JDBC driver is the most strategic piece besides distributed joins that is going to come. Yep. Yes. if we get to that point, so I suspect that our bottleneck is just going to be the amount of data on the network. And I don't know, if we ever get to the point where the transport mechanism is really the bottleneck, then maybe we'd switch it. There are other people who care about that more than me too. There are people who want to move to the next version of Jetty and use different ways of sending data. That's not my main focus. So if it happens, it most likely would happen by somebody else. I have. So I've read some of the Spark stuff. It's hard. I'm not a Spark expert by any stretch. It's hard for me to comment on how this differs from Spark. I don't know if you can comment on it.
No, I just thought the whole premise was this last issue talking about
Yeah.
trying to be more intelligent about when you're going to cross.
Okay. So this is how I see that though. So to be more intelligent, you decide when you're going to push down. So shuffling should be a last resort. So you only shuffle when you have to. If you can do 90% of your stuff pushing down, you got no network problems at all. So I think that might be my answer to that, the resilient stuff. I don't know how good Spark is at pushing down. I'm not sure. Spark has a different problem in that they have lots of different things they connect to, and it's very hard to push down to lots of different things. You can push certain things down, but you can't push shuffling down, or things like that. So, and also sometimes it's hard to push down aggregations on some engines. So, Solr, you can push a lot of stuff down. Yep. It is not. There are tickets out there for it. So distributed joins change the way that we are operating. So to give you an example, let's say we're doing an aggregation on a distributed join. The query plan for that would be significantly different than doing an aggregation off of one index. And so the next step is to build an optimizer. Done? We're done. Build an optimizer is the next step. All right, thanks guys.